in the PG less than 10 to the minus 6 torr. So generally, no chemical reaction because there's the vacuum is very high or pressure is very low. So no gas. And there's no gas, there's no chemical reaction. And we understand in the Rubin square is about 10 meters, and which is a Leucian number which is larger than 1. And in that situation, the evaporation have poor stat coverage. And okay, so the pressure mostly let's skip this. So this is a ultra high vacuum chamber. This is a viewport where you can see through. Okay, and this is difficult to see, but this is a low lock, a gate valve. This is a gate valve. Next week, I'm going to show you some vacuum devices in our lab so that you can see better. This is not easy to see. So we talk about the Nusselt number, okay, and this is a Nusselt number 10, and this is roughly 10 to the minus 4, and if this is a region for the sputtering, and this is a region for the green part is a region's operating window for the CVD, which is quite large, and the sputtering very small, very limited. And the fabrication, you see, the fabrication has to be ballistic molecular flow. Okay, and so the pressure low and the mean free path, which is larger than the chamber length. Okay, and you have a high purity film. Okay. So with 10 to the minus 6 torr of water vapor at room temperature, what will be the flux? The flux will be somewhere around 4.8 times 10 to the 14. So what does that mean? What does that mean? That means if there is a little bit water, okay, in the surface, and make it to the 10 to the minus 6 torr, you will see there's quite a large of flux, water atoms per centimeter square per second. And we talk about that, the atomic density in one monolayer of silicon. The number of silicon is 5 times 10 to the 22 per cubic centimeter. Okay, and so if one monolayer, and we understand at 10 to the minus 6 torr, one monolayer of residual gas hit the surface every 3 seconds, which means it's very difficult to keep in the ultra high vacuum. So epitaxy requires slow deposition, high surface mobility. And you must keep pressure low, maintain pure film. Okay. So this is a evaporation source. This is the most widely used resistive heater, and this is your your materials, which is ready to be evaporated. And this is a coil, the coil of RF coil, and so this is RF heating, and this is using a filament through a magnetic field, B field, hit on um, the the target. So this we call the E beam. We call the E beam. Okay, and uh, this is a work function. The work function, right? And to remove it to the vacuum, the free vacuum, right? So how do we do that? How do we do that? Um, we need to know that the heat of evaporation is a key to remove from the liquid phase, solid phase to liquid phase, and finally to the vapor phase. So the elemental metals are easy to evaporate, but this alloy and the compound are difficult. Okay, so and very challenging because they have different saturated pressure, right? Because their boiling point are different. So maybe you can use two crucibles, right? Or using something multi-layer and deposit multi-layer. Okay. The oxide or nitrides, we have to deposit in oxygen, nitrogen, partial pressure. But this is difficult to make because in the evaporation, we normally make a very low pressure. So this is a challenge. This is a challenge. You can after that you can go to the to go the link and find. We will talk about the source and how it become a flux. Okay, next week. I just give you a roughly idea, and so this is a crucible, and this is the target that we want to evaporate. And regarding to the evaporation, we always consider about the how it strikes on the substrate. So how much evaporant strikes on substrate? Like this is a substrate, so there is a limited, and it's hit on a theta degrees. And this is another way, and we hit on put the substrate in this way, and we can calculate how much it hit on the surface. Okay, so this is a very key issue. We need to make sure the we know if it is better to keep substrate here or keep the substrate here or substrate here or here or here. So we need to do normally engineer will do some calculation and calculate the geometric factor. Okay, this is a geometric factor. And this is a planetary substrate heater. This is a convenient type of geometry. And it's quite easy to calculate because You got the theta 1 and theta 1 and theta 2. And the film growth rate for evaporation is, you can see, is proportional to the, if you got the T source, you got the T source and M source, okay, proportional to the M source. So, and also this is a cross-section area and the pressure, okay, vapor pressure. So this is how we do the calculation. And in the PVD growth, the strike balance of the deposition rate over the surface diffusion rate. We talk about that, right? So R greater than 1 is stochastic growth, quite rough. If R less than 1, that will become layer by layer, and that will be smooth. So these are simple calculation. And we talk about that. The stack coverage is poor in evaporation because the molecules, gas molecules is in the bolastic flow, which is the pressure is quite low. And then in that case, you will have you found that there is a shadow effect because there is the direction is not in a certain degrees, and this is the hole. We found that you got the layer deposition on here, but not here. This is a shadow effect. So how to solve this problem? There is one easy part. You can heat the substrate. When you heat the substrate, the diffusion, the temperature increase, you got a D increase. So surface diffusion increase. Surface diffusion increase, this can migrate to here. So this is how we do it. So by contrast, metal CVD and sputtering can do a better job. So we didn't use evaporation for this kind of trench, but we do use CVD and sputtering for the trench because they provide a better step coverage. So this is a heating type you need to memorize. And this is quite a good picture showing the microstructure types in the sputter film, which increasing substrate temperature. When you increase substrate temperature, you found something in different way. Okay, this is a cranch growth, and this is a thermally activated growth. Okay, so this is quite interesting, and you see this have a clear grain, here. Okay, so so increasing the temperature, and you will see this is a layer, island, and homogeneous and crystalline. So we have 4 characteristics about equilibrium. This is a phase diagram. Okay, this is a phase diagram, and the interface between this Miller's material, which make a non-equilibrium. This is suddenly you have an A and B together, but this is like you put a metal, cobalt copper or cobalt gold. This is another, is you see the diffusion, okay, like a nickel copper, nickel chromium. This is quite um, uh, unusual, I think. It's a pity that there is a hold, okay, um, and ethereum. And this is something like uh, reaction, reaction, like gallium arsenide, the compound, the gallium arsenide compound forms at interface. And this is something like a DB diffuse into A and make A swells, and the swells into back to B as a second phase. This is quite interesting. And this is how the stress and the strain and stress 力跟应力应变应力 and from here you got the yield. So when you get the small stress, you are strain 应变 and then going back, it won't come back. So this is called the yield. And when it defracts from the this straight line, we call the plastic deformation. And when you reducing the stress, it go back like this, and we call this is a Young modulus. Okay. So upon thermal cycling, a film deposited under the condition and leave a tensile stress, tension, compression. And so when you are heating, keep heating, and you found that the stress may evolve through compression and then even greater tension. So you got a higher, make it higher tension, more than original. Okay, so like something like this. Okay, and this part is tension. This part is compression. So you got the tension to the compression, 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 tension, higher tension. So the evaporation, what we can talk about the evaporation is quite quite less. So this is the only part that you can we can talk about the evaporation. Okay, so I think this is the end of today's talk. And next week, for the first hour, I will probably give you a review about what I talked this week. Okay, because this week I give you something